Welcome back to Arxflix. Today, we're exploring a groundbreaking paper titled Implicit Self-Improvement for Large Language Models. This research tackles the challenge of enhancing the quality of large language model (LLM) responses without relying on extensive human annotation. LLMs have achieved remarkable success on various tasks, but their open-ended nature means there's always room for improvement. Traditional approaches like instruction fine-tuning and reinforcement learning from human feedback, RLHF, are effective, but they require vast amounts of human effort, especially for domain-specific tasks. This has led to a focus on enabling LLMs to self-improve their responses. Prompting-based methods have gained popularity, but they often require explicitly defined rubrics, which can be challenging to create for complex improvement goals. This figure illustrates the difference between traditional prompting methods and the proposed Implicit Self-Improvement (PIT) framework. PIT leverages preference data to implicitly learn improvement goals, eliminating the need for explicit rubrics. PIT reformulates the RLHF training objective. Instead of maximizing response quality for a given input, it maximizes the quality gap between a response and a reference response. This implicitly trains the model to align with human preferences and improve its responses. PIT consists of three main components: supervised fine-tuning, reward model training, and reinforcement learning. Supervised fine-tuning, SFT, is a prerequisite step where the model is trained to generate responses that resemble human-written ones. The reward model learns to assess the quality gap between two responses. It's trained on preference data, where pairs of responses are labeled as better or worse. This equation defines the reward gap, which is the difference in quality between two responses, y and y2, for a given input, x. Reinforcement learning, RL, optimizes the model to maximize the expected reward gap over time. This aligns the model's responses with human preferences. PIT employs curriculum reinforcement learning, gradually increasing the difficulty of the optimization problem. It starts by training the model to improve ground truth responses, and then progresses to improving responses generated by the policy model itself. The paper evaluates PIT on three datasets: Anthropic HHRLHF, OpenAI summary, and a synthetic dataset. It compares PIT with prompting-based methods like self-refine. PIT consistently outperforms original responses and prompting-based methods, demonstrating its effectiveness in improving response quality. The paper investigates the impact of temperature on self-improvement. Lower temperatures generally lead to better performance for PIT, as it focuses on a single, reliable improvement direction. Experiments show that curriculum reinforcement learning is crucial for PIT's success. Removing the initial training phase on ground truth responses significantly hinders the model's ability to improve responses. The paper explores the impact of multiple improvement iterations. While PIT consistently outperforms self-refine, the optimal number of iterations is not straightforward and requires careful consideration in real-world applications. PIT offers a promising approach to implicit self-improvement for LLMs. It eliminates the need for explicit rubrics and leverages preference data to learn improvement goals. The paper highlights the importance of curriculum reinforcement learning and the need for further research on stop conditions for self-improvement. That's a wrap for this paper summary. If you found this video helpful, please give it a thumbs up and subscribe to Arxflix for more insightful breakdowns of cutting-edge research. Thanks for watching. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.